So to start off, we're going to be talking about the photon. The photon is basically a small packet of light. It has a wavelength and a frequency, but it also acts as a particle as well. So it's both. It acts as both a wave and a particle. Photons are massless, and they travel at the speed of light in a vacuum. Photons are the base of electromagnetic radiation, and they're the smallest unit of it. So they make up all light and UV, IR, visible light as well. Yeah. So the energy of a photon can be calculated by using the formula E equals hf, where h is Planck's constant, which is equal to 6.63 times 10 to the negative 34. So in that equation, we find out that energy is proportional to frequency. So the more times it vibrates during each second, the more energy that photon has. Okay, sweet. The next slide we've got is on the quantization of energy. Energy can only exist in discrete energy levels. In this context, discrete means non-continuous. So, for example, particles can have 1 joule of energy or 2 joules of energy, but not 1.3 joules of energy. That's obviously not a realistic example, but you can also use the analogy of a gearbox in a car. So you can only be in gear 1 or gear 2 or gear 3, but not gear 1.5. So light is also quantized into photons. So photons have specific energy that is based on their frequency, and that doesn't change. Yeah, so go to this one. So discrete atomic energy levels. This is a modern physics principle based on the Bohr's model of the atom, which says that there is a dense region of positive charge, which is called the nucleus, and it's filled with nucleons, protons and neutrons. And then that is orbited by electrons, and they orbit in discrete shells. Electrons will always try to stay in the lowest energy state, which is the shell closest to the nucleus. If that shell becomes full, they'll start filling up the shells further away from the nucleus, but for the most part they try to stay in that's called the ground state. They can change energy levels though by absorbing or emitting energy. Emitted energy is almost always in the form of photons, and same with absorbing, but it can also be other forms of energy. So electron shells, they're discrete amounts of energy. So an electron in one shell will always have the same amount of energy as other electrons in that shell, for each element, that is. But which means that they can only have certain levels, and they cannot exist between energy levels. Electron shells are also fixed in space, so they're a fixed distance from the nucleus and don't change. It also is worth mentioning that energy shells are different for each element. So hydrogen will have different energy levels than helium and such like. So electron transitions. For this concept to make sense, it needs to be previous concepts need to be understood, such as electrons can only exist in discrete energy levels and not in between. Electrons can jump between energy levels by absorbing or releasing specific amounts of energy. That's called a quantum quantum leap. The energy absorbed is usually in the form of a photon, but it can also absorb other types of energy as well, such as electricity. So the energy that is absorbed needs to have an exact amount of energy for the electron to be able to absorb it, because if the photon has more energy or less energy, the electron would end up in between energy levels, and it just can't exist in between energy levels. So the energy must have a specific amount for the electron to be able to absorb it and jump up into a higher energy level. Electron energy for a hydrogen atom can be calculated using the equation E, energy level, equals negative CHR over energy level squared. So in this equation, C is the speed of light, R is Rydberg's constant, and H is Planck's constant, which you have seen already. So energy of released or absorbed photon is equal to the difference in energy of the two energy levels. We'll see an example of this on the next slide, but for now, we'll just have to keep that concept in mind. So in this equation, if n equals infinity, then the result will always be 0, because when you divide by 0, divide by infinity, the answer will always be 0. So I think I missed something here. Oh yeah, if photons have a different amount of energy than the electron needs, the photon will just pass through the energy, pass through the electron. Yeah, that's it. So in this example, there is 2 electrons in different energy levels. There's this electron in the first energy level on the left, and the electron on the third energy level on the right. The one on the left has an energy of negative 2.19 times 10 to the negative 18, and the one on the right has an energy of negative 2.4 times 10 to the negative 19. So the one on the left looks like it has less energy because it's a smaller number closer to 0, but actually it has more energy because it's a negative, so a closer number to 0 will be more energy than the one on the left, which is further away from 0. So the energy required for an electron to jump between energy level 1 and energy level 3 is the difference in these two numbers here. Also, if it was to go from energy level 3 to energy level 1, it would have to release that amount of energy in the form of a photon. So here we see Rydberg's equation, which is specific for hydrogen atoms. So there are multiple series here. There's Lyman, Balmer, Paschen, and Beckett series. The released photon will have a wavelength that is visible to human eyes. So that's what's special about the Balmer series. But this equation here can be used to calculate any electron change, emission of any photon between any energy level change. So it can be calculated to 3 when electrons drop to energy level 3 or 4 or 1 or anything there. So in this equation, we've got 1 over wavelengths equals Rydberg's constant, which is equal to, what does it say there, 1.00 times 10 to the 7. And then we've got it times by 1 over the series, aka the energy level that the electron is dropping to squared, minus 1 over the line, which is where the energy level where it started, squared. Okay, so the photoelectric effect is the complete removal of an electron from an atom. This is usually observed in metals because they have low work functions, which we'll talk about later. But this can be observed when shining light with sufficient frequency or specific wavelengths onto the atom. This is only practical with metals because, as I said before, the wavelengths of other elements are way too high for this to be observed. But yeah. Ejected electrons are called photoelectrons. Okay, so the work function is the amount of energy holding the electron in the atom. The work function is different for each element. So silicon will have a different work function than iron, for example. Electrons absorb light with more energy. Wait, what? Electrons absorb light with more energy than the work function and then are ejected. So the energy from the light is converted into kinetic energy for the photoelectron. So the total energy, the energy of the photon is equal to the work function plus the kinetic energy of the photoelectron. So if you rearrange that equation, you get kinetic energy is equal to the energy of the photon minus the work function. So each electron can only absorb one incident photon at a time. This is quite an important concept. So increasing the intensity of the light does not increase the kinetic energy of the photoelectron, but it does mean that more electrons can absorb more photons. So we get a higher release volume of photoelectrons. That which increases the current. So V0 is what is known as the threshold frequency. The threshold frequency is the minimum frequency required to remove an electron from the atom. Okay, so as we'll see in the next slide, the electrodes that absorb the photons and the ones that release the electrons, can be charged. So if we look here, so the emitter can be charged and so can the collector. So if the emitter is negatively charged and the collector is positively charged, the electrons will be pushed away from the emitter because like charges repel. The opposite can also be achieved though. So the stopping voltage is the minimum negative voltage required to stop electrons from reaching the collector. So this occurs when the emitter is positively charged and the collector is negatively charged, which means the electrons are attracted back into the emitter. Atomic line spectra. This can be done using discharge tubes, which are glass tubes with electrodes at each end. It is filled with low pressure gas that a current can be run through. So when you run a high voltage current through them, the gas will emit light. So some of these will be visible, especially in hydrogen, the Balmer series in particular. If a small beam, electrons absorb the electric current to be promoted and then drop back down to lower energy levels to release photons with certain wavelengths. So if a small beam is split with a prism, the pattern that shows is called the emission spectra. This will show a series of colored bars with only specific wavelengths. of where the electrons dropped from high energy levels back down the energy levels. So say one dropped from energy level 4 to energy level 2, the wavelength released from that will be visible. Every element's emission spectra is unique, so this allows analysis of the light from gases to match it to already known spectra. Absorption spectra are like emission spectra, but the opposite. So you can do it by shining white light through the cold gas in the discharge tube without running a current through it. Because white light contains all the wavelengths, the electrons can only absorb the wavelengths, and when it drops back down to the energy levels, it doesn't emit enough light to be able to be visible. So when the light has passed through the discharge tube, the photons released from energy electrons dropping down get scattered too much for it to be seen. If light has been passed through the discharge tube, it is split with a prism, and the pattern will be the inverse of the emission spectra, which means that there'll be continuous color with black bars where absorption occurs instead of black with colored bars. And only certain wavelengths are absorbed, so that explains the very thin black bars that are there. So this is an example of an emission spectra of hydrogen. The absorption is at the top and the emission is at the bottom. Okay, so applications of electron transitions. There are two main applications, and that is neon lights. These are created by bending glass tubes into shapes and filling them with low-pressure gases. Different gases can be used to have different emission spectra, so you can achieve different colors by putting different gases into the tubes. Another application is spectroscopy of stars. So each chemical element has unique emission and absorption spectra. Light from stars or white light that passes through nebula can be analyzed and compared to known emission spectra. Nebula are just large bodies of gas and dust floating in space, but the light given off by stars can be split using massive telescopes, such as the Very Large Telescope in Chile. The resulting spectra can be analyzed and elements can be assigned to each star. The thickness of the lines can also be used to determine the velocity of the star, because wider gaps will mean sort of like redshifting, but with this. White light contains all wavelengths, so when it goes through the nebula, the nebula absorbs some of that light by only specific wavelengths, and an absorption spectra is made. And applications of the photoelectric effect. Light meters. They're also known as lux meters. They detect how much light is present in an environment. These devices use the photoelectric effect to do this. The greater the current produced by the photoelectric cell, the light there is in an environment. So pretty much the intensity of the light means that there are more photoelectrons and more current is produced. So the greater the current, of course, the lux meter will detect a greater current and then give a different reading of how much light there is in an environment. Yeah, that is it. So, yeah. Sweet, thanks.